So now we're going to use what we saw previously, those basic notions for reinforcement learning, and we're going to apply these to these problems of deep reinforcement learning, where basically we call it deep because we use deep learning to solve the reinforcement learning problems. I'm going to give a brief introduction to what kind of problems we solve with deep reinforcement learning, then look at the exploration and exploitation problem, how we gather data, balancing, trying to find new options and using the knowledge the agent already has. And then we're going to see how we can learn policies using deep neural networks. Then I'm going to show you an example to solve the cart pole problem, which is basically trying to balance a pole on top of a cart that can move in one direction. And I'm going to talk about the second assignment, which is going to be on deep reinforcement learning. So let's start with linking this to what we saw previously. So if we know the Markov decision process, that is, we know the policy, we know the probabilities of changing states given actions at each state, we know the rewards for all the states and so on, so we know everything, we can compute the state value function, the V function for a policy. We have that iterative evaluation where we start at random and then we keep updating, and we can figure out how much each state, how much is the expected return at each state for that particular policy. Using that, we can compute the Q function, which is the action value function that tells us for each state, for each action, what is the expected return, discounted return, if we take that action in that state. And given that, we can improve the policy, because if the policy is telling us to choose an action at some particular state, but we know from the Q function that there is a better action at that particular state, we can replace it in the policy, and so we can train our agent using this method and improve the policy gradually. Of course, this only works if we know the full Markov decision process. That is, the policies, the states, the probabilities of transitions, the rewards, and so on. We have everything there, and so we can do these computations. We need basically to have a complete information about the states of the systems and must be able to enumerate all of these values and states and actions. We have this table. For example, the Q function would be a large table with all the combinations of states and actions giving us the expected return. This is not something that we can generally do when we have realistic cases, because realistic cases can have too many states. For example, consider here the breakout game. Even if we consider that the positions of all the elements are discrete because they are in pixels, this game has a huge number of different states, and it will not be practical to have a table with all possible actions and all possible states. Also, we can have continuous problems. Here we are trying to balance this pole on top of this little cart that goes from left to right, and this can be a continuous problem because of the position and the velocity and the force we are impacting on the cart and so on. So we cannot enumerate all the possible states of this problem. So what we're going to see here is how we can combine the basic ideas that we saw, where we have the Q function as a large table telling us which action is best at each, or the expected return for each action at each state, and we can choose the best one and so on. And we're going to try to approximate this. Instead of having a large table, we're going to approximate this function with a neural network. That way we can deal with situations where the number of states is too large, or there are continuous states and so forth. The network will try to approximate as best as possible the best Q function, the optimal Q function. So some features of deep reinforcement learning that distinguish it from deep supervised and unsupervised learning. One is that we have a delayed feedback. Since we cannot look at the full Markov decision process and we don't have the ground truth for each decision. So what would be the ideal decision? We need to rely on events, on the experiences the agent will gather in sequences of actions. And often when we do some action and get into some state, we don't immediately get the reward for that because we need some additional actions until we reach a state that gives us the reward. So this feedback on how well things are going is often delayed and needs to be credited to the appropriate actions. Also, the feedback is evaluative. In supervised learning, we have some target that we are going to try to approximate. So we know what the output of the network should have been in that particular example if the network was correct. And that is an absolute value. It must be this value. In reinforcement learning, what we have is relative feedback. So an evaluation that if we choose this action, we get a greater reward than if we should choose that other one. But we don't have necessarily an example that tells us this is the best possible outcome. We don't have directly that feedback of what the best possible thing is or what the right answer should be. We also don't have the complete decision problem. So we have only samples of actions that and corresponding rewards that depend on how we explore the state and action space, the possibilities of actions and states. So basically, while in supervised learning or even unsupervised learning in practice in deep learning, we have a data set and we are using that data set for fitting the model. We may have problems generalizing outside of it, but we are fitting the model to that particular data set. In reinforcement learning, we, as the agent learns, we keep sampling the state and action space to see if we can find better things. And also, not necessarily, so these three first features are really characteristic of deep reinforcement learning. Another thing is usually the case in the interesting problems is that we do not have an observation that corresponds directly to the actual state or to the relevant attributes in the state. Sometimes we do. If you are training a chess playing program, for example, you can input into your network the actual description of the positions of the pieces on the boards. But often we are dealing with sensors or images or things like that. For example, if you want to train the agent to drive a car or to play StarCraft or something like that, you need to start with unstructured data from your sensors, from your images. And so you also need the deep network to extract the appropriate features that describe the state and then manage to approximate the Q function. So let's look first at this problem of balancing exploration and exploitation. We are not using a fixed data set, and as the agent learns, we can explore more of the system. So suppose that you have an agent that starts just playing randomly. It will not advance too much on the level of some game, or it will not be able to play up to some particular stage in chess or something like that. As the agent learns, you can go further in the rewards, get more rewards because you can choose actions better and advance more in whatever task the agent is doing. However, if we exploit that agent's knowledge to guide the exploration, we can go further in the task, but we'll be always following the same recipe because we are just following the policy the agent already has. And this does not allow the agent to find better things, better alternatives. In alternative, we can risk going outside the policy of the agent. So the agent tells us that for that state, it's best to do some particular action, but we choose some other action at random. This may be a bad idea because if you play at random, you're not playing very good in a game, or if you drive at random, you're likely to smash the car against some obstacle. But if we do that, if we go outside what the agent is thinking is best to do, we may find alternatives that are even better than what the agent had learned. So there is a trade-off between these two, exploration and exploitation. Exploration allows us to find new things. Exploitation allows us to take advantage of what the agent already learned to progress more in the problem. Different ways of balancing this is, for example, these are just examples. There are many different ways, but to give you an idea, epsilon greedy exploration is greedy in the sense that it favors the exploitation part. We tend to follow what the agent thinks it's best to do, but with some small epsilon probability, we deviate from what the agent wants to do and, for example, randomize the action at that stage. So most of the time we are following the agent's recommendations, but with a probability epsilon, we take a random guess and do something different. A variant of this is to use decaying epsilon greedy exploration, where the epsilon value may start large. In the beginning of training, the agent is not very good anyway, so we can just go random a lot of times and gather data about what the outcome of that will be. But then as the agent improves, we are gradually reducing epsilon until we reach a small but non-zero value. So it's not a good idea to set epsilon to 0, because then there will be no exploration of new options and we are just following the agent. So decaying epsilon greedy exploration starts with a large epsilon and then reduces it to a small value during training. We can also do a different approach, which is using the initialization of the Q function. So suppose that we actually have a Q function in a table. This is the best way to imagine this. We set high values to everything. So basically we are being optimistic. We're saying that for any state and action, if we do that action in that state, we get a large reward. As we start training, we start finding out that the reward is much smaller than what we were expecting. So as we choose actions and get feedback from the system, the values for those state action pairs in the Q function will decrease. But some actions that we did not try will still have the large initial values. So following the recommendations of the agent will naturally lead us to explore new combinations of action values, because we are being optimistic and we say, okay, these ones are all bad, but we never tried this one and this one seems great, so let's try it now. This is the idea of optimistic initialization. Another approach is when we have our Q function that is telling us the expected return for each action in a particular state, instead of just using the best action, the one with the largest Q value, we use those Q values in a softmax function and use that softmax as a probability. So when you use softmax, the largest values will get the largest probability and the smallest one the smaller probability. So if we use select at random from that distribution with those probabilities, we are still favoring the action the agent considers best. But if there is some uncertainty, there are some second best actions with a large probability, then often we will pick those and so keep exploring using the agent recommendations, not as a deterministic policy that tells us choose the best one, but as a probabilistic policy with this softmax distribution. So this incorporates exploration in the decisions of the agent. Another approach is to use a measure of uncertainty. So this is given all the time steps that we've taken, what is the fraction of times we chose action A? If we chose action A a very small number of times, this will be a large term, and as we add this to the expected return of choosing action A at state S, so this is the Q function that tells us what to expect for discounted future rewards and the overall return if we choose A at state S. But we add this uncertainty term that will make it will favor actions that we didn't try too many times before. Uh, and so basically we are doing something that is a bit optimistic. If we didn't try this too many times, then maybe it will work well. But within some boundary, we use this. This value can be adjusted C so that we give a relative weight to this uncertainty. And basically, if we use this, we are still using the recommendation of the agent, but also including some additional factor to encourage exploring new actions that we didn't try as frequently before. Okay, so now let's see how we can learn policies in deep reinforcement learning. We cannot use the same iterative policy evaluation approach that we saw in the previous lecture, because that using the policy to compute the state value function, the V, and then using the V to compute the Q function, the action value function, so that we can improve the policy, only works if we know the complete Markov decision process. We have all the states, all the probabilities of transitions, the rewards, everything. We don't have that in realistic cases, but we can still take advantage of this definition of these state value and action value functions. So remember that the state value function gives us the expected return for that particular state. And this is the reward that we get when we go from this state to another following our policy pi, plus the discounted return we will get from that state, which is in the future, all the way to the end. So this is the discounted return for state S. Now, if we compute this, let's say we have a policy. Our policy is telling us to take a step to a new state when we are in this particular state. We have a reward when we take that step. And we can use the same function that we have here to evaluate what should the additional return be with that discount. And this should be the same thing. So basically, we can consider this to be the target value for our state value function. This is what the state value function is actually telling us that is the value at state S. And this would be an error if these don't match. So if the reward added to the estimate of the future returns is not the same as the estimate of the returns at this state, we have an error in our state value function. So we could improve our state value function. If the state value function is actually a table, for example, we can take a small step, some learning rate, to fix this error. So we take the previous value, the estimates using the previous value of the state value function, and if these things don't match, the estimate and the target estimate, we correct it slightly in that direction, and we iteratively improve our state value function. So this could be a way of improving the state value function without knowing the complete MDP. Basically, we are using the information we are getting from the system via the rewards to adjust our estimates of what the future returns should be. And even though the rewards only occur occasionally in some states, this will propagate through the different states because the states will be related to, each state will be related to other states according to the policy that we're following that gives us actions to go from one state to the other. More interestingly, we can do the same thing for the action value function, the Q function. So we can consider that the estimated future return for taking action T at state S would be the reward we get plus the discounted future returns of starting from that state. Now we can consider that this future return would be from the state that we are now in, the future state. We follow the policy, and so we have a new action at that state. and we go check the Q function to see what would be the expected return at that new state following our policy. So this is the target value. What we expect to be the future return of taking action A at state S should be the reward we get from that action plus the discounted future expected return if from the next state we take the action the policy tells us to take and go on. So this should be the same as this. If it's not, if there is a difference, then we have an error here and we can do the update. So we take the value that we had previously on our state action function, our table for all the actions and all the states, and we update it with the difference between what the result should have been and what the result is. So this is the state action reward state action algorithm, or SARSA algorithm, where we are taking this reward following the action and considering what would be the future returns if we keep following the policy. So this is what we use to update our Q function. An alternative is to use the Q-learning algorithm, which is similar, but now we are considering that the expected returns in the future are the optimal ones. So we get the reward by taking this action and this step, and then we consider the discounted value of the maximum that we can have by taking the best possible action in the next step. So we are taking the maximum of the expected return on the next step, considering all the different actions that we can take. And if this is different from what we are estimating, then we don't have the optimal Q function here. So we can improve our Q function by adjusting it with some learning rate and keep doing this iteratively. So this is also, there is a difference between SARSA and Q-learning. We say that SARSA is a non-policy algorithm because it considers that the future expected return for the next state will be given by the policy. So we are using the action that the policy recommends. Q-learning is off policy because we are now ignoring the policy here and we are choosing the best possible action. So we are trying to go faster to the optimal Q function. But this is this tells us how we can keep updating the function if we have the function, for example, in a table and we can adjust the values immediately. With deep reinforcement learning, we do not have the Q function in a table. So we cannot really do this. We cannot just adjust the value with a small step in the right direction. But we can use the fact that this would be the target value. So if things were working well, that is, if we had the optimal Q function, then this estimated return of at this state with this action would be exactly this value here. It would be the reward we get and the estimated return by taking the best possible action at the next state. So we can consider that this is a target, or if we keep inside the policy, we can consider that this is a target for learning. And so we can use this to train our network. Basically, what we're going to do is to create a deep neural network that will tell us, will approximate the Q function. So the input is the observation of the state. We have this input here. We need to know the state in which we are. And we will output not one value. So naively, we could think of this network as taking the state and all the actions as input, or the state and one action as input, and then outputting the action value, the value of the Q function for that pair state action. But this would not be very practical because then we would need to feed different actions into the network and so on. It's best to do it like this. The input to the network is just the observation of the state, and the output is one linear neuron for each action. So basically, we are outputting for each action the value of the Q function for that particular state. And so we use a linear activation of the output because this is a regression problem. We want the output of the neuron for action A at state S to be as close as possible to the optimal state value function for that action to the optimal action value function, so the optimal Q function for that action at that particular state. So we need a linear activation, and we can use, for example, mean squared error or something equivalent. We'll see in the example there are some better options, but the idea is to try to minimize the error between what the optimal value should be and what the value we are outputting from the network. Of course, we don't have this optimal value. So if we could figure out what is the optimal Q function, then the problem would be easy to solve. But that is the difficulty. We don't have the optimal value, but we can try to approximate it iteratively. So the question is, what data do we use to train the network? We need the input, the features. So this would be an X matrix with all the states that we observe in a mini batch, for example. And now we need the target values for the network. What would be the Q values that the network will have to learn for each action? We do this by gathering experiences. That is, we take a step in the game or in the system that we are trying to learn to navigate, and we store the state in which we are, the action that we chose, the next state that we got into, the rewards that we got by that transition, and whether or not we reach the terminal state. It's important to know if we reach the terminal state for the future return estimates. So this would be the tuple that describes its experience. We went from state ST to state ST plus 1, taking action AT. We got reward RT, and this tells us whether or not we reached a terminal state in state T plus 1. And now we can use this, the action, the next state, the reward, and the data on the terminal to estimate what the Y value should be. So if we use the SARS algorithm, then the target value would be this one here. This is what our our action value function should have output, and this is what we would use to compute the error and do the correction. So if you're training the network to try to output that value, this should be the target. And we can get this by computing the estimating the future returns of the next state when we take the action that the policy recommends for the next state, and using the same network that we have. So we can just pass through the next state that we got in our network, get the estimated returns for all the actions, pick the action that we would naturally pick on that state, and then use this as the discounted future return. We add this to the reward that we got on this particular action, and this is what the network should output when we input the state that we are in, and this would be the output for the particular action that we chose. Of course, it's best to use Q-learning. So this would be following the policy, but generally, if the policy is to pick the action with the maximum value, maybe these two will not be different in our particular implementation. But we're generally going to use Q-learning, which is we simply take the maximum value for the next step. So we are going to give our network the next state, get all the action values for all the different actions, and compute the maximum of that. So this would be the maximum expected return that our network is giving us for the next state. And what we would want our network to output for this state S would be the reward that we get here plus the discounted value of this future return. So this is the target, the Y that we can get for training in each particular example. So given the X, which is the state S, the Y would be the return we got when using this action and the discounted expected return for the best action in the future step. Now, one particular detail here that is important to remember is that this is only the adjustment for this particular action. Remember that our network is outputting the Q values estimated for all the different actions. So for the other actions, the ones that we did not choose in this particular experience, we need to keep the value the same. We don't want to adjust those. We just want to do this for this particular action. But we're going to see this in more detail in the code in this example. This is the cart pull problem. Imagine that we have a cart here that is sliding without resistance, and we can push the cart to one side or the other by applying a force. If we keep applying the force to the same side, the cart accelerates. If we then push to the other side, the cart will slow down. And we have to do this to keep the pole close to the vertical. If the pole deviates 15 degrees from the vertical or the cart slides too far away from the center, the game stops. And we get increasing rewards the longer we last balancing the pole with the cart. So this is the cart pole v1 scenario in the OpenAI library in the gym. You can install that and you can use this. And I'm going to adapt a tutorial that you can find by Mike Wang in this site. So first we're going to import what we need. We're going to use Keras to create the network that tries to predict the expected returns of pushing left or pushing right, which are the actions that we have. We're going to use a double Q to keep a collection of experiences. The double Q is an object that you can specify. It's like a list, but it's optimized for inserting and removing at either end. And you can specify a maximum size. And as you keep appending new elements, if you start going over the maximum size, the double Q will discard older elements automatically and keep that size. So this is where we're going to store all the experiences we gathered so far, and we're going to store a large number, 50,000 experiences, from which we're going to sample the training batches. But we're going to add new experiences as the training progresses. Basically, we're going to create this environment, the cart pole v1 environment, and this is where we're going to get the state and we're going to act on that environment. Okay, so this is the model for the agent. We start with a dense layer of 24 neurons. The input shape is the size of the input that we get from the environment there. And then we have another layer with 12 neurons, and at the end we have a layer that has as many neurons as the action. So in this case, it's only two actions, push left or push right. So we have these two neurons that will try to output the expected return of doing that particular action in the state that we receive as input. Now, there are a few adjustments here. So we could use the mean squared error function, but in this tutorial, they found that the Huber loss function is better. Huber is similar to mean squared error, but instead of increasing quadratically, when we have a large error, it increases linearly. So it doesn't respond so strongly to large outliers, and it seems to work a bit better for this example. Another tweaking that they did is to use this he-uniform initializers, which initializes the weights using a uniform distribution of in the range of plus and minus 6 divided by the square root of the number of inputs into the layer. So this, you remember, we talked about these initialization functions. This is just one that Keras has available, but these are just details that you can fiddle with to try to optimize the model. But basically, this is a neural network with 3 layers, and the important thing is that the input is what the observation is, the observation that the environment is giving us, and the output is a number of neurons equal to the number of actions that we have, and we are trying to output the expected return of taking that action in the state that was input into the network. So basically, we are trying to learn the Q function, the action value function, for this problem. So now for training, what we do is we have the environment. The environment is what we can use to interact with. This replay memory is the list of previous experiences, and each experience is this tuple here. You have the observation of the state that we started from, which action was taken in that state, what was the reward that was gained in the new state, and what is the new state that we fell into, and whether or not this was a terminal state. So a terminal state here is a state when the pole becomes too unbalanced, over 15 degrees away from the vertical, or the cart slides too far away from the center of the rail. And so for training, we can sample randomly from the memory of experiences. We have a large list of these tuples. We're going to sample at random to create a mini batch. And now we're going to create the X values. So basically the X is a list of observations for all of these experiences. The observation is the observation of the state we were starting from. And the Y values, which are the targets that we're going to use to adjust our network, will be, if the state is a terminal state, it will just be the reward we get from reaching that state. This is because when we reach a terminal state, future rewards will be 0. We cannot advance from there, so there is no more reward in the future other than whatever reward we got from reaching that state. If it's not a terminal state, then what we're going to do is the expected return will be the reward that we have, and then the discounted expected return for the future. And what we're going to do that is we're going to use the estimate that we get from our model. So we're going to predict from the new states, the new observations that we have here, we are going to predict what the expected return would be for the different actions. And we're going to use that prediction, but since this is Q-learning, we're going to use the maximum of those predictions. So we are going to think about what is the expected return if we choose the best possible action in the next state. We're going to discount that by the discount factor, and this is the target for our network. Our network should be outputting that for the action that we chose. And now we're going to create this y. So look, remember that this epsilon value has the predictions that we are making for the new state here, the future predictions, but we are just going to change the value, adjust the value for the action that we chose. The other actions we retain, we are not going to adjust them because those were not the actions chosen in this experience. Now, one particular detail here is you notice that we are using this target model for the predictions of the future expected result instead of the actual model for our agent, the model we are using to decide on each action. The reason for this, and this is a trick here, is that they are using one model for the agent. So this is the real model, the one that is deciding how to act, and the one that is being trained. And they are creating a copy of this to give us the target values for the future expected return. And the reason for this is that if we use the same model, we have a problem that as we train the model, then these expected returns will immediately change, and then we immediately get new expected values on the next batch, and so on and so on. So the target for our network keeps changing very quickly, and this sometimes makes training a bit harder. So what they did to improve that is to use a model that is simply a copy of the main model. This target model is a copy of the main model. It is not trained, but it is updated once in a while. So here, if after 100 steps, the target model is updated with a copy of the main model. So basically you can imagine that this target model is delayed with respect to the main model, and it's always about 100 steps behind, so that it provides more stable targets for the training of the main model. This is one example of the kinds of tricks that we can use to improve the training in these deep reinforcement learning problems. So basically, this is what is being done here, using this target model to estimate the future return after we take this step, and adjust that by the reward. The reward is given by the system. So this is where reality comes into our training process. And then we use that to create the target values for this batch and then fit the model. Remember also that we are just changing the target value for the action that we took. The other actions we keep the same value so that we do not change them in examples where those actions were not taken. And each example is one experience which goes from one observation to taking some action, and this will get us some reward and expected future returns. So the main loop here, we create the model for our agent. We copy that model into the target model. We create this pool for examples, which has a maximum of 50,000 experiences there. And now we will follow the steps of the game. So basically, we reset the game for each episode. Each episode, in this case, is a complete game, trying to balance the pole until it falls. And now we can take some action. And depending on this epsilon value, this is a decaying epsilon greedy exploration, where the epsilon starts at 1, but then decays gradually until it's only 1% here. But depending on where we are, if the random number is lower or equal to epsilon, we take a random action. Otherwise, we take the action predicted by the model. So we take the observation the state that we have here. We create a batch with this single state. We use the predict method to predict the Q values for each action at this state. And now we take the action that corresponds to the maximum of those Q values. Now the new observation, the reward, and the flag that tells us if it's done or not, this is given by the step method in the environment. So this environment is what is actually playing the card pull game. We give it the action and it tells us what happens. This info is a dictionary with additional information, but we don't use that for training. This can be for debugging, for testing, things like that. And now we append this tuple with the old observation, the action, the reward, the new observation, and the flag that tells us when we reach a terminal state. We append this to the pool of examples that we have. Since this double queue has a maximum size of 50,000, until it reaches 50,000, we are just appending new examples. Once it reaches 50,000, it starts discarding the older examples and we start renewing them with the new examples. So now we check if we have at least this number 1,000 examples. So we only start training if we have at least 1,000 examples in the pool, so that we can start drawing examples at random for the mini batches. And in that case, every 4 steps, we train our main model with a mini batch of examples. And if we reach the end of an episode, that is, the game is finished, then we will need to reset the episode and so on, but that is done here outside the loop. This, while not done, keeps the episode all the way to the end. Once it's done, we reset the episode and restart the game. But also at this stage, we check how we increment the step and check if we want to update the target model. So basically the target model gets updated after a number of episodes, the 100 episodes, and updating the target model is simply copying the weights from the main model. This means that basically we are using the same model for predicting future returns and for training the agent. The only thing is that the prediction of future returns is delayed and doesn't update as often, so that we have a more stable prediction for the model to converge to. These parameters, or whether or not this works, depends on the actual problem, but this is just to give you an idea of the kinds of things that we can do to try to improve training here. And now we decay the epsilon so that we decrease the probability of taking random steps, and we keep doing this for a number of episodes. Okay, so this is the tutorial that we're going to do today to try to optimize, to get the network to learn how to predict the expected return for each action, so that then we can decide how to act when playing this card pull game. For the assignment, the motivation is to train the snake player. So this is an example of one agent that I got. It's a bit frustrating because it takes a long time to go for the food, but I used a very large discount factor, so maybe that was one of the problems. You can experiment with that, but basically this is not the goal of the assignment. This is just a motivation. We want to train an agent to play the snake game, and this is what motivates the rest of the assignment. The actual goals is for you to explore different approaches, different options, different networks. You can use the Q-learning algorithm, or you can look for alternatives. There are many different alternatives to solve the reinforcement learning, deep reinforcement learning. This is a very rapidly expanding field, so any algorithm that you learn today in a few weeks may be outdated. So the most important thing is to be familiarized with the problems and gain some practice looking up different approaches, because if you're interested in this field, that will be the most important thing. So try different schedules of the exploration and exploitation balance, different ways of storing the experiences, and so on. And this to understand the problems that we have in this particular case. For example, the rewards are fairly rare, because only when the agent finds food do we get a reward. And it can easily happen that you have an agent that just loops around and doesn't do anything and just keeps forever going in circles, things like that. So look at what happens when you're trying to train your agent. Think about the problem and learn to get an intuitive feeling for these kinds of problems. So grading will depend a lot on your explanations of your approaches, your what you experimented, what were the things that you were attempting to do. So those of you who took the machine learning course last semester, if you remember, the second assignment was also very much open-ended, where you had to figure out what usefulness could have in clustering those cell images. This is similar in spirit. The idea is for you to explore this problem and try different approaches and understand what you're trying to do and what you can do to improve the results. So the main goal will be to give you this intuitive understanding of deep reinforcement learning, of the problems that we have, of different approaches, and feel free to explore the solutions for this problem as you wish. So this will all depend on the snake game. You have this class called snake game that implements the reset and the step methods that you have in the OpenAI environment. So you'll use it in a similar way that you use these different examples that you can find in tutorials. And so when you take a step, you get the new state that the board is left in, the reward for this step, a flag that tells you if you reach the terminal state. So if you leave the board or you touch the snake tail, the game is over. And this is some information. It just gives you the total score so far, but you're not going to use this for learning. You get this on the step, and on the reset method you also get this return. The board state is a NumPy array where you have height times width times 3. So this is a color image. It's exactly the images I was showing in the animation. The snake, the tail is red and the head is white. The food is green, and if you create a border, you can optionally add a border to the map, and this would be gray. So this can help finding the edges and avoiding the edges, or not, so you can experiment with this. But you have an option there to add a border outside around the board of the game with a number of cells that you specify. So you can even do this because it's difficult for the snake to find the food. You can experiment with changing the size of the board, and if you want to keep the images of the same size, for example, for training your network, you can adjust the size of the board and the border so that the image is always the same size, but you can squeeze the snake into smaller regions. So you can experiment with this if you want to try to improve the examples that you get or the training. Just don't try to go too small, because there is some we need some space to set the tail of the snake at the beginning and the position of the food and so on. So I'd say around 14 should work. Less than that, maybe you start getting some errors. But if you use too small a board and get an error, just increase the size. I would say the goal would be this one, 30 by 30. This is what I used. 30 by 30, the size of the board. Then you add a border of 1, so you get an image of 32 by 32 pixels, which is good for convolutional networks and doing max pooling and so on. So this would be a recommendation, but you can experiment with larger or smaller boards if you want. There is no rigid goal here. This is just a motivation for the experiment. Another problem is that since the rewards are rare, we can have agents that just spin around and don't do anything. So one of the things that I implemented in the game is to have grass growing. You can specify what is the maximum the grass can grow and how much it grows on each step. And this will return a small reward for the agent every time the head passes over grass. So it feeds on grass and then it gets a larger reward of one in the food. But this is one way of encouraging the agent to explore more and not just loop around in the same place. Also, I used a smaller decay function, the decay value, discount value, the gamma value. So this agent is a bit more greedy, trying to find the food. But this is one way we can solve this problem of having rare rewards. We give a small reward for exploration, and this increases the odds of finding the food and learning that it's good to eat. Another solution that I tried was to populate the initial pool of examples. Instead of using random actions, use a simple heuristic. So I use a simple heuristic to always go towards the food. This is not a good strategy because the agent dies a lot, but it increases the number of examples that you have, of experiences that you have in the training pool where the agent finds food and gets reward. So this teaches the network to associate the food with the reward better. So one example of a trick, this is not things that you are that I'm telling you to do, that you must do, but just examples of things that you can experiment with and will help you gain some understanding of what works and what are the results of different things. So this is, to do this, you can use this cheat here, which is a get state function method on the snake game that gives you the actual state of the board. So what the score is, where the apples, the food are. You can use more than one. So by default there is only one food item at a time, one apple at a time. But you can increase that if you want to try to train with more food, so that it's easier to find food. You can increase here, and this get state method gives you the list of coordinates for all the apples, where the head of the snake is, the tail, and the current direction of the snake. So this is not what you should use for training. You should use just the image of the board so that the network learns to figure out where the snake is going and figure out the actions. By the way, the actions that you have here, I forgot to put here, but you have three actions, which are -1, 0, and 1. -1 turns left, 0 keeps going in the same direction, and 1 turns right. So in order to decide the direction, your network must learn to figure out where the snake is going. For example, in this case, if we pick -1, the snake will start going down. If we pick 0, the snake will continue straight ahead. If we pick 1, the snake will turn up. But these are just the three actions that you have, and they will be dependent on where the snake is going. So if you want to shortcut this to get some heuristic or something like that, you also have the current direction here that will help you figure out what the next step should be. But you should not use this for training the network. This is only if you want to experiment with things like populating with different examples the initial pool or something like that, then you can use this, but not for actual training. And this is an example of what I got with an initial pool created by those heuristics, an heuristic that went straight ahead to the apple, and also a very large discount factor. So this was, I think, 0.99. So the agent is not very worried about when it gets to the food, and sometimes it's a bit frustrating because it takes quite a large roundabout way before getting to the apple. But this is another aspect that you can experiment with to try to optimize the performance. So this can take a while to train, especially if you have large boards, and because playing, it's not so much training time, so you don't need to have powerful graphic cards and things like that, but it's just playing the game. Playing the game takes some time because you have to do a prediction and then do an iteration of the game and so forth. So you can start experiment with smaller boards and go increasingly larger until you are confident that you can just let it train for 1 or 2 hours, something like that. I will post the detailed instructions during this week. Also, those files that you have to fill in when submitting the assignment. I will put everything there, just like for the first assignment. But the code is already available. You just need the snake game to start experimenting. So today you can start experimenting with the second assignment, although I recommend that you do first the tutorial for the card pull, just to get a feeling for the different how the things work, and then the snake game will work the same as one of these environments. So just start playing with that one. I will post the instructions, the details, and those files during this week. The deadline is June 10, so there is over 2 weeks yet for this, and with the customary 48 hours of tolerance for solving any submission problems. Okay, so we saw this step from reinforcement learning, where in abstract, in theory, we have all the Markov decision process and we can do all the computations. We step from that into deep reinforcement learning, where we don't have an explicit Q function, we have an approximation given by the neural network, and how we can adapt those learning algorithms so that we can train the neural network. This balance between exploring new options and exploiting the knowledge of the agent, how we improve policy. So basically, we're going to use deep Q learning, adapting the Q learning algorithm to training our deep neural network. And we saw the poll card example and the second assignment. So for this part, you can read chapters 4, 5, 6, and 8 of this book. Optionally, note that the book goes into much more detail. What I covered here was just what I could do in 2 hours. But this is actually an interesting book. It's well written and has both the mathematics and code examples to make it easy to understand. So if you're interested in reinforcement learning, I would recommend taking a look at this book, and this can give you more ideas for the assignment. So what you invest in the assignment will depend a bit on your interest here, but the important part for grading will be your explanations and your reasoning and how you understand these problems. Okay, so this took a bit more than it should. I'm going to log into Zoom in case any of you have questions, or you can just proceed to the tutorial if you don't have questions. See you soon.